on yn. So these y values, that means these y values are not always the same, these f of x0, f of x1, f of x2, and so on, f of xn values. So that means this yi is equal to this yi, that means y0 is equal to this y0 equal to this f of x0 plus e. So y0 is equal to f of x0 plus e. So the difference between y0 and f of x0 is nothing but the error will develop. So that is the difference to the tabular values, where we took the tabular values in the previous classes and in this lesson. So here we are going to take this type of tabular values, x, x0, x1, and so on, xn, y0, y1, and so on, yn. These y values are not always the same, these f of x values. So that means this y value is equal to this f of x value plus some error. So that means we can say that this error incurred in the measurement. This is denoted as the measurement. So now we can consider this one as, in these situations, interpolation polynomial which we have obtained so far will not be of much use, so that it is enough that an approximating function whose graph is passing very close to the graph of the data points. For example, in the previous classes, which we have taken the tabular values and we can draw the graph. So now in this class, in this unit, we are taking the tabular values like this, according to this table. So here also, using this tabular values, we can draw the graph. But that means it is enough that this is an approximating function. The graph of this function is passing very close to the graph of this function, this function of the given tabular values. So this means here we consider an approximate function which graph is close to the graph of the function which is related to the given data points. Now, in this case, it is possible to recover the polynomial function from such an approximate data. This process is called curve fitting. So this process is called the curve fitting. In this unit, you will be able to fit a desired curve for a given data. So in this unit, what will you do? You will be able to fit a desired curve for a given data. That means you will learn the method of approximation, method of approximating functions. So you are going to learn the method of approximating functions that fits with the given data, by least squares approximation through first degree polynomial or second degree polynomial or a non-polynomial function. This method is known as method of least squares approximation. So this method is known as method of least squares approximation. Method of least squares approximation. Using this method, you will do that least squares approximation using this method. So you are going to find the least squares approximation for fitting a straight line. For fitting a straight line, that is y is equal to a plus bx, where a and b are parameters. That means fitting a straight line means fitting a first degree polynomial to the given data. So straight line means first degree polynomial to the given data. That means least square approximation for fitting a first degree polynomial. So is this first degree polynomial? This is the first degree polynomial in X. Straight line means first degree polynomial to the given data. Similarly, you are going to find least squares approximation for fitting a parabola. That is, it is denoted by y is equal to a plus bx plus cx square. Here, a, b, c are parameters. That is, so least squares of fitting a parabola. Fitting a parabola means fitting a second degree polynomial. A second degree polynomial to the given data. Now, similarly, you are also going to find a least squares approximation for fitting a curve y is equal to a into x to the power m. Here m is not a parameter. It is a fixed number, some number, not a parameter. Here a is a parameter. And similarly, you are also going to find a least squares approximation for fitting an exponential curve. That is, y is equal to a into e to the power bx. Here a and b are parameters. So these 4 points. You are going to study all these 4 points. So that means you are going to find a approximation first degree polynomial. That is straight line. You are going to find a approximation second degree polynomial. So that is parabola. And you are going to find a least squares approximation to fit a curve y is equal to a x to the power m. And similarly, y is equal to a e to the power bx. This is the exponential function. So now first we are going to discuss about least squares approximation for a straight line. Or also we can say that least squares approximation by a first degree polynomial. We can say that least squares approximation for a straight line or by a first degree polynomial. So now we will discuss about least squares approximation for a straight line or first degree polynomial. Let y is equal to f of x be a function. We know that. And let xi, yi, where I is equal to, here I am taking from 1, 2, and so on, comma. So here I am not taking 0 for our convenient. So here x values are x1, x2, and so on, xn, n values. From x1, x2, and so on, xn. How many values are there? N values. Here I am taking the x values from x1 to xn. And y values are from y1 to yn. So there are n values. Be the given. So far, we have taken the tabular values from x0 to xn and y0 to yn. There are n plus 1 values. Here, I am taking only n values from x0 to xn and y0 to yn for our convenient. So be the given pairs of observed values. So you can take these x values from x0 to xn. That means n plus 1 values. We can take also. So we can take from n plus 1 values or n values from x0 to xn or x1 to xn. So whichever values we can take, there is nothing to worry to take the values. So now here let f of x is equal to a plus bx. You know that this is the first degree polynomial. Be a first degree polynomial. Or we can say that this is a straight line. So this first degree polynomial approximation, suppose here I am assuming this first degree polynomial approximation to the function or polynomial of the given data. Whichever data they will be given. So this is the function or polynomial of the given data. So this is the assuming polynomial, first degree polynomial. This assuming polynomial is a first degree polynomial. This is approximate to the original polynomial which is related to the given data. So we are assuming this. Now, here we are talking about these values are observed values. yi values are observed values. And now, the estimated values for y1, y2, and so on, comma, yn. Here, the values are y1, y2, and so on, yn. So that for y1, y2, and so on, yn, the estimated values are, what is y1? Y equal to a plus, f of x equal to a plus bx. So estimated value is y equal to a plus bx. y1 is equal to a plus bx1, comma, y2 is equal to a plus bx2, comma, and so on, comma, yn is equal to a plus bxn, respectively. Now, hence, the deviations between observed values and the estimated values can be written as observed values minus estimated values. The observed value minus the estimated value is the deviation. So that can be written as, hence the deviations denoted by di. For I equal to 1, d1, I equal to 2, d2. So hence the deviations between the observed values. What are the observed values? y1, y2, and so on, yn. And the estimated values. What are the estimated values? A plus B xi, A plus B x1, A plus B x2, and so on, A plus B xn. Can be written as di is equal to yi minus A plus B xi. So this means that the difference of observed value and estimated value is nothing but the deviation. Y1 minus A plus B x1 is equal to D1. Y2 minus A plus B x2 is equal to D2. So and so on. Yn minus A plus B xn is equal to Dn. So for that, here we are taking di is equal to yi minus A plus B xi, where I is equal to 1, 2, and so on, n. Now, the sum of here, we take square on both sides. And then we take the sum of square deviations. So now we take square on both sides for I equal to 1, for I equal to 2, and so on for I equal to n. So there are n deviations, d1, d2, and so on, dn. So now sum of all the deviations. We take the sum of all the deviations, d1 plus d2 plus and so on plus dn. And the sum of deviations, take square on both sides. So that means we can write it as the sum of the square deviations. Between the observed values and estimated values is. Okay. So what is the sum of this one? Summation dA. d1 plus d2 plus and so on plus dn. This is equal to. What is the sum of the right side part? The summation of yi minus A plus B xi. Like this. This is the sum of all the right side terms. This is the sum of all the left side terms, d1, d2, and so on, dn. d1 plus, this means I is equal to 1 to n, d1, that means, okay. Now we can write, take I equal to 1 to n, I equal to 1 to n. Now take square on both sides of this one. We will get this one as summation I is equal to 1 to n. So di square is equal to summation I is equal to 1 to n yi minus A plus B xi. This is the summation of the left side part and right side part, and take the square on both sides. We will get like this. Give equation number 1 for this one. Next one, here we can observe that since the right hand side is a function, okay, the right hand side of this equation 1 is the function of A and B. So that we can write it as, since the right hand side of equation 1 is a function of A and B. Now, we shall denote it as capital S of A comma B, so that we can write the above equation 1 as S, capital S, is equal to summation I is equal to 1 to n yi minus A plus B xi whole square. Now, according to the principle of least squares, we have to determine the parameters A and B so that we can say that this one is going to a minimum value. According to the principle of least squares, we have to determine according to the principle of least squares. Here we have to determine the parameters. A, how many parameters are there? A and B. A and B, so that S is a minimum value. That is, for S to have a minimum, for S to have a minimum value, we require its first order partial derivatives. Partial derivatives with respect to A and B. Two parameters A and B are there, so that we can differentiate this one with respect to partially, with respect to A and B partially, to be 0. The value is minimum means to be 0. So that is, this means that S to be a minimum, we have to require that the first order partial derivatives with respect to A and B to be 0. So that means this is the condition. So what is the first order partial derivative of S with respect to A? Dou S by dou this capital S. Dou S by dou A. And the partial derivative of this S with respect to B is dou S by dou B. So both are equal to 0. So this is the condition to become S is a minimum. Okay. Now, now we follow this condition. What is dou S by dou A? From equation 2, give equation number 2. From equation 2, we have first differentiate this equation to partially with respect to A, that is dou S by dou A is equal 0. The first condition, this condition, dou S by dou A is equal to 0. So now, what is dou S by dou A? Partially differentiate partially equation 2 with respect to A. Dou S by dou A value. What is the dou S by dou A? So differentiate this partially with respect to A to get dou S by dou A. So you know that ordinary derivative of x to the power n d by dx of x to the power n is x to the power n minus 1. Similarly, dou by dou x of x to the power n is n into x to the power n minus 1. So you apply this formula here. So this is x square in the form of x square. Dou by dou x of x square means 2 into x. So apply this formula means dou S by dou A is equal 0. Dou S by dou A value is, so this is x to the power n in the form of x to the power n. That is 2. What is n? 2. 2 into yi minus a plus b xi. 2 into x. What is x again? So what is this? Coefficient of x is nothing but b. So b will come. What is this one? Coefficient of a. Here we are taking the differentiate partially with respect to a. So with respect to a means dou a by dou a. That is 1. Dou by dou a of bxi is nothing but 0. So only 2 will come. Summation I equal to 1 to n will come. Is equal to 0. So this follows that summation yi is equal to summation I equal to 1 to n a plus b xi. We can write this one as summation I equal to 1 to n a plus summation I equal to 1 to n bxi. Therefore, summation I equal to 1 to n yi is equal to, this one is equal to, so what is a? I equal to 1 to n times of a. Summation of a from I equal to 1 to n means n times of a, na, plus b into b is a constant parameter. Summation I equal to 1 to n xi. Give equation number 3. Now I am going to take another page. Now, what is the remaining part? We got it, dou s by dou a value, and dou s by dou a is equal to 0. We get equation 3. And similarly, we can find dou s by dou b. That means differentiating equation 2 partially with respect to b, we get dou s by dou b. The condition is here dou s by dou b is equal to 0. And find the value of dou s by dou b from equation 2. So dou by dou b of right side part of equation 2. So that is in the form of dou by dou b of x to the power n into x to the power n minus 1. So like that, you apply that formula here. So 2 into yi minus a plus b xi. Summation as it is. It will come as it is. And with respect to b here, so partial differentiation with respect to b. So that b is the, what is b? Coefficient of xi. So that xi is the coefficient of bi. Xi will come as it is. This one is equal to 0 like this. Now simplify this one. Summation I is equal to 1 to n xi. So multiply this term with xi. Xi into yi is equal to summation I equal to 1 to n a plus b xi into xi. Now we can write it as summation I equal to 1 to n a xi plus summation I equal to 1 to n b xi into xi square. Therefore, summation I equal to 1 to n xi into yi is equal to, take a out, take a into summation I equal to 1 to n xi plus b, take out b because b is a parameter, summation I equal to 1 to n xi whole square. A and b are parameters. Give equation number 4 for this one. Now, observe equation 3 and equation 4. These equations 3 and 4 are called normal equations. Normal equations. These two equations, 3 and 4 equations, are called normal equations for the least squares approximation. Least squares approximation by the first degree. Or you can say that for the straight line, that is for fitting a straight line. Here, the number of normal equations is how many parameters are there in the assumption of polynomial a in a plus bx, y equal to a plus bx. So a and b are parameters, 2 parameters. So here the number of normal equations is equal to the number of parameters. So how many normal equations are here? 2, equation 3 and equation 4. So the number of normal equations is equal to the number of parameters in the assumption polynomial. After getting these set of normal equations, we have to do the following concept. So next what will we do after getting these two normal equations? So first we have to observe that here, what is the given data? So what is the given data? The given data is xi comma yi, where I is equal to 1, 2, and so on. N. So the given data is x1, x2, and so on, xn as x values, y1, y2, and so on, yn are the y values. So this is the given data. So now use these tabular values, to find the required sums in equations 3 and 4. So observe equation 3 and 4. First, in the equation 4, the sum of xi into yi. The sum of, so summation of xi, this one. So this is the summation of xi square. So if you observe the third equation, what is the equation 3? So this in this one, this is the summation yi and this is the summation xi. So using the given data, we have to find the required sums, that is summation yi, summation xi, and next the summation xi yi, and summation xi already came in the equation 3, and summation xi square. So now we have to find all these summations by using the given tabular values. So after getting these summations, we have to substitute that relevant summations in equations 3 and 4. So after doing this, we will get some linear equations in A and B, in parameters A and B. Anyway, at that time, we have 2 linear equations in A and B. So that means after that, we can get the values of A and B by solving that 2 linear equations. After getting the values of A and B, we have to substitute these A and B values in this one. Assumption polynomial f of x is equal to a plus bx. So after substituting the A and B values in this assumption polynomial, so we get the required least squares approximation, that is known as the least squares approximation by first degree polynomial, or so it is going to fit a straight line like that. So now I am going to give the data here for your convenience. So the given data is this one, and by substituting the tabular values in equations 3 and 4, and then simplify. Then we will get two simultaneous linear equations in two parameters, A and B. On solving these equations, we get the values of A and B. So now substitute these values of A and B in the equation or polynomial. Y is equal to f of x is equal to ax plus b. Then this is a least squares, or well, then we get, sorry, you can write, then we get the least squares approximation. Then we get the required. We get the required least squares approximation for a straight line or by a first degree polynomial. For a straight line of best fit to the given data. So this is the required least squares approximation for a straight line. Next, we go to take example under this concept. So using this concept, we take one example here. Find the least squares approximation by a first degree polynomial or a straight line. To the given data, to the given following data. So now this is the given data. Take x values as well as y values. X values are 2, 4, 6, 8, 10, and 12. Y values are 7.32, 8.24, 9.20, 10.19, 11.01, 12.05. Next, solution. So first, what will we do, ma?
Tabular values.
First, we have to assume the polynomial or straight line. We have to assume it. That is, let the straight line which is to be fitted to the given data. Given data ku fit అయ్యే విధంగా ఉండే straight line ని ఒకటి మనం assume చేసుకుంటున్నాం. So let us assume that the straight line is y is equal to a plus bx. So give equation number 1 for this. Now, first you have to observe this from the given problem. How many values are there? 1, 2, 3, 4, 5, 6. How many x values are there? 6. How many y values are there? 6. So n is equal to here 6. Here we have the 6 tabular values. So therefore the number of values is 6. That is n is equal to 6. Now here to find these parameters a and b, we have to take the normal equations from the procedure which I have explained just now. So now for the desired polynomial, the normal equations are. So what are the normal equations? How many normal equations are there, ma? 2 normal equations in the above procedure. So directly you can take that 2 normal equations, equation 3 and equation 4 in the above procedure, normal equations. Therefore, first you have to take normal equations. The normal equations for the desired polynomial are the normal. So these are the normal equations which are useful for finding the approximating polynomial. So what are these normal equations for straight line? So the procedure which I have explained just now, from that you have to take that 2 normal equations. So in that procedure, equation 3 and equation 4 are called normal equations. So what are these 2 normal equations, ma? This one, equation 4 and equation 3, this one. This equation 3, take this equation. Summation y is equal to n into a plus b summation x. So the next normal equation is summation x into y is equal to, here I equal to 1 to 6, n is equal to 6. So no need to write. Summation x into y is equal to a into summation x plus b into summation x square. No need to write I in the problem. Because here n equal to 6. Okay, here you can write the normal equation. Summation y is equal to n into a plus b into summation x. And summation xy is equal to a into summation x plus b into summation x square. Give equation number 2. Now, to find the values of parameters a and b, we have to find the sums which are in the normal equations, too. So how many sums are there? Summation x is there, summation y is there, summation x, summation y, summation xy, or summation x square, and summation xy. So we have to find all these. How can we find these values? So we are going to use the table for finding these values. So according to the table, take x values. These are given tabular values. According to the given data, take x values as 2, 4, 6, 8, 10, 12. Take y values from the given data 7.32, 8.24, 9.20, 10.19, 11.01, 12.05. First, we are going to find. So from this one, we can get summation x. From this one, we can get summation y. Summation x means sum of all the x values. And summation y means sum of all the y values. First, let me know about the summation x. Sum of all the x values. What is that value, ma?
42.
42. What is the summation of y? Sum of all the y values. Use the calculator and find it. 7.32 plus 8.24 plus 9.20 plus 10.19 plus 11.01 plus 12.05. Summation y. Sum of all the y values.
58.01.
Yes, right. 58.01. Next, summation x square. That means take x square values first.
4,
4,
16,
16,
36,
36, 64, 100, 144. Sum of x square. Summation x square is nothing but sum of all the x square values.
$364.
364. Very good. Next, take xy values. X into y, 7.32 into 2.
14.64.
14.64. Next, 8.24 into 4.
32.96.
32.96. Very good. Next, 9.20 into 6.
55.2.
55.2. Next, 10.19 into 8.
81.52.
Next value.
110.1.
Yes, right. Next value.
144.6.
Very good. 144.6. Next, what is the sum of all these values? That is summation xy. $439.
439.02.
Very good. 439.02. Now, substituting all these values in the normal equations too. So, in the normal equations too, what are the normal equations?
Y equals to
Summation y is equal to NA into NA plus summation y. What is summation y? 58.01 is equal to NA. What is N ma? 6. 6 into A plus summation x. Summation x into
42.
42 into B. First equation. In that, the second equation is summation xy. What is summation xy? 439.02 is equal to a into summation x. That is 42 into a plus b into summation x square. Summation x square is 364 into b. Now, to find a and b values, so this is the linear equation in a and b. This is also the linear equation in a and b. We can solve both the equations for getting the values of a and b. So solve these two equations for a and b values. First multiply equation 1 by 7 and then solve the first and second equation. You can get the b value.
But equation 3 and 4 అని ఇచ్చుకోవచ్చు కదా మేడం.
Yeah, you can give you equation 3 and 4. Solve these equations 3 and 4.
$406.07.
'b' value ma?
కాదు మేడం 58.01 into 7 కి.
Oh, okay. You have to solve it, ma.
Okay.
Directly you say that the values of a and b. Shall I give the values? Anybody, ma? Did you get it? B value? 0.4704. And substitute b value in equation 1, you can get a value. That is 6.3734. Okay?
Okay.
Okay. So now what will we do after getting a and b values? We have to substitute these values in the equation 1. That is y is equal to a plus bx.
Yes.
Now, substituting the values of a and b in equation 1. We get y is equal to 6.3734a plus bx, 0.4707x. This is the required least square approximation. Okay. This is they require least square approximation. To the given data. Or you can also, this is the required straight line to be fit with given data. So now page number 96, in page number 96, so you do that example as follows, this same procedure, this procedure.
Okay, ma'am.
Next, I am going to take least squares approximation for a parabolic fit or a second degree polynomial. The same procedure we have to follow, which I have explained, least square approximation for a first degree or for a straight line for a first degree polynomial. So now, least squares approximation, next concept, for a parabolic fit or parabolic function, or least squares approximation by a second degree polynomial or quadratic polynomial, second degree polynomial or quadratic polynomial or parabola, first degree polynomial or straight line. So we have to follow the same procedure as above. Let y is equal to f of x be a function, and suppose that xi, yi, where I equal to 1, 2, and so on, n, be the given pair of observed values. So that means this is the given data, x1, x2, and so on, xn, y1, y2, and so on, yn. So these given data, these values are called observed values in this concept. We are calling these one like this. Let f of x is equal to a plus bx plus cx square, second degree polynomial. This is the second degree polynomial or parabola or quadratic polynomial, quadratic function. So a plus bx plus cx square be the second degree polynomial or quadratic or parabolic function. Approximation, this second degree polynomial approximation to the function or polynomial of the given data. So this is the approximate polynomial. This second degree polynomial is the approximate polynomial to the polynomial of the given data. So here we are assuming this one. Now the estimated values for y1, y2, and so on, yn. For these y1, y2, and so on, yn, the estimated values are a plus bx1 plus cx1 square, a plus bx1 plus cx1 square. For y2, the estimated value is a plus bx2 plus cx2 square, and so on. For yn, the estimated value is a plus bxn plus cxn whole square, respectively. Now, the difference of observed value and the estimated value, y1 minus this y1 minus this one, and this y2 minus this one, this observed value yn minus this estimated value, this one. So the difference of observed value and estimated value is known as the deviation. So here we can write it as, hence the deviation. So here there are n deviations, so that we can write dl, I equal to 1 to n, because there are n deviations, y1, y2, and so on, yn, and this one, and so on, this one, n, between the observed values, that is yi, y1, y2, and so on, yn, and estimated values. Estimated values. What are the estimated values? A plus bxi plus cxi whole square. Can be written as same procedure as we have explained just now in the case of straight line. di is equal to yi, the difference between observed value minus estimated value, a plus bxi plus cxi square. Now here, so d1, d2, and so on, dn, n deviations are there. So n, the difference between observed value and estimated values are n values are there. So now we take the sum of deviations, that is d1 plus d2 plus and so on plus dn. So if you take square on both sides after getting the sum, we can write it as then the sum of the squared deviations. First take square on both sides and then take the sum of all the values from left as well as from both. We can write it as summation di square, d1 square plus d2 square plus and so on plus dn square. I is equal to 1 to n. This is equal to summation I is equal to 1 to n yi minus a plus bxi plus cxi square whole square. So we know that RH is the right hand side part in this one. This is a function of A, B, and C. Since the right hand side is a function of 3 parameters, A, B, and C, so that we shall denote it as capital S of A, B, C. Hence, so here for our convenience, it is denoted by S of A, B, C. Hence, S of A, B, C is equal to summation I is equal to 1 to n yi minus A plus bxi plus cxi whole square. Cxi square total whole square. Now, the same give equation number 1 for this one and 2 for this one. According to the principle of least squares,
partial derivative.
According to the principle of least squares, we have to determine the parameters A, B, and C. We have to determine the parameters A, B, and C so that S is minimum. It has a minimum value. So that is, this means that for S to be a minimum, we have to require its first order partial derivatives with respect to A, B, and C to be 0. So to be 0, that is the partial derivative of S with respect to A is dou S by dou A, and the partial derivative of S with respect to B, that is dou S by dou B. The partial derivative of S with respect to C, that is dou S by dou C, is equal to 0. This is the condition for S to be a minimum value. Now, from equation 2, we will get the partial derivatives dou S by dou A, dou S by dou B, dou S by dou C. After getting partial derivatives, we have to equating to 0 all these. So then we will get our required equations. Hence, from equation 2, we have dou S by dou A. What is dou S by dou A value? It is equating to 0 for S to be minimum. So now we will find dou S by dou A. That means partial derivative of S with respect to A. So differentiate this with respect to A partially. What is this? 2 into summation. So this is in the form of x to the power n. Dou by dou x. That is n into x to the power n minus 1. Summation I is equal to 1 to n yi. So this is n. What is n here? 2. 2 into. So what is x? This one. Yi minus a plus bxi plus cxi square. So this is differentiating with respect to a. So dou a by dou a becomes 1. So this is into 1. That is 1. Next, this is equal to 0. From this expression, we can write it as summation from I is equal to 1 to n, yi is equal to summation I is equal to from 1 to n, a plus bxi plus cxi square. This is also equal to summation I is equal to from 1 to n a plus summation I is equal to 1 to n b xi plus summation I is equal to 1 to n c xi square. We can simplify this one. So now finally, summation I is equal to 1 to n, yi is equal to, what is this a? N times of a. From 1 to n, there are n a's are there. That means n times of a plus a plus a plus and so on, n times, that is n into a. Na plus b is a parameter, constant. A, b, c are parameters. From the second term, b is a parameter. We can take out b into summation I is equal to 1 to n xi plus C is also parameter from we can from the third term we can take C like C into I is equal to 1 to n xi square. Give equation number 3. In the same procedure, we like this, we have to find dou S by dou B equal to 0 and dou S by dou C equal to 0 and then simplify this one.
Excuse me, madam. ఇంతకుముందు పేపర్ ఒకసారి పెడతారా మేడం? స్క్రీన్ షాట్ తీసుకుని. ఓకే మేడం, థ్యాంక్ యూ.
So now I will take another phase for getting the value of dou S by dou B. What is dou S by dou B, ma? So observe here that, sorry, the phase number, this phase, dou S minus A. This is minus A. Minus of dou A by dou A will come minus 1. So minus 2 should be there. Sorry. Minus 2 should be there like this. Where it is? Minus. Like here. So minus 2 will be there. So according to this one, differentiate S, that is equation 2, partially with respect to B. So then we can get as minus 2, first 2 into summation I equal to 1 to n yi minus A plus bxi plus cxi square. And again, minus of bxi can be differentiated partially. So that means this is partial derivative with respect to b, so that we can have minus of xi. Minus will come like this, xi will come like this, is equal to 0. Which implies that we can simplify this one. So multiply this one throughout with xi. That is summation I equal to 1 to n xi yi is equal to, take this part to the right side. Summation I equal to 1 to n a plus bxi plus cxi square into xi. Now we can simplify this one. That means we can multiply this one by xi. That is summation I equal to 1 to n a xi plus summation I equal to 1 to n b xi into xi square plus summation I equal to 1 to n c xi square into xi cube. Therefore, summation I equal to 1 to n xi yi is equal to a, b, c are parameters. We can take out a, b, c from summation. A into summation I equal from 1 to n xi plus b into summation I equal to 1 to n xi square plus c into summation I equal to 1 to n xi whole cube. Give equation number 4. What is the previous equation number 3? So it can be taken as 4. Now, similarly, we can find dou S by dou C value. It is going to be 0. So what is this? Differentiate equation 2 with respect to C partially. We get dou S by dou C. What is dou S by dou C value? 2 into summation I equal to 1 to n. Follow the same procedure. Apply the derivative of x to the power n formula. yi minus a plus bxi plus cxi square
into xi square.
So now again differentiate partially dou by dou c of minus of cx square. So minus of cxi square can be differentiated with respect to c partially. The remaining part is minus xi square. So therefore now we can simplify this one and multiply this one throughout by xi square. That is summation I equal from 1 to n xi square yi is equal to take this term to the right side. Summation I equal to 1 to n a xi square plus summation I equal to 1 to n b xi into xi square xi cube plus summation I equal to 1 to n c xi square into xi square xi to the power 4. Therefore, summation I equal to 1 to n xi square yi is equal to take a, b, c out from the summation, that is a into summation I equal to 1 to n xi square plus b into summation I equal to 1 xi cube plus c into summation I equal from 1 to n xi to the power 4. Give equation number 5. So how many parameters are there in our assumption polynomial? 3. A,
3.
B, C. So that definitely we should have 3 normal equations. Equation 3, 4 and 5 are called the normal equations. These three equations are called normal equations for the second degree polynomial. So therefore, these 3 equations, 3, 4 and 5 are called normal equations for the second degree. Polynomial. For the second degree polynomial. Or also you can say that parabolic least squares approximation. These 3 are normal equations for parabolic least squares approximation. These are the normal equations for parabolic least squares approximation, or these are the normal equations for the second degree polynomial. So after completing these normal equations, after finding these normal equations, we have to find the values of parameters A, B and C. How can we find these values of A, B and C? So here we have to use the given tabular values. By using the given tabular values from equation 3, 4 and 5, we have to find the relevant summations or required summations. From equation 5, summation xi square yi is there, summation xi square is there, summation xi cube is there, summation xi4 is there. From this equation 4, summation xi yi is there, and summation x already, these are in equation 5. And next, another equation, equation 3. Where is equation 3? This one. From this one, summation yi is there, summation xi is there. Already this is in another equation. So anyway, we have to find all these required summations by using the values. After getting that, we will get 3 simultaneous linear equations in A, B, and C. So solving these 3 equations, we can get the values of A and B. After getting the values of A, B, and C, all these values are substituting in the equation 1, that is y equal to a plus bx plus cx square. So this that after that we will call it as required second degree polynomial or required parabolic approximation, least squares approximation. Now these 3 equations, 3, 4, and 5, can be solved by finding the required summation by using the given tabular values. Then we will get the values of A, B, and C, and then substitute these values of A, B, and C in y is equal to f of x is equal to a plus bx plus cx square. Then we obtain the required least square approximation for second degree polynomial, or for parabolic least square approximation, whichever we can say that. Call it as this one. So next there is an example under this problem. So there is no sufficient time. Time is already over. So anyway, I will give you example for this concept and later I will discuss another unit in next class. Okay, ma?
Okay.